So this video is on the complexity of selection sort, and finally, this is very easy to understand what the complexity of selection sort is, because it behaves always the same. There's no difference between the arrays, so it's totally independent of the initial order of the elements. So in all cases, it will do this outer loop. So this outer loop will make n many iterations, and in all cases, in each iteration of this outer loop, this inner loop will make n minus k many iterations. K is the iteration of the outer loop. So because the purpose of this inner loop is just to find out for the rest of the array what is the minimal value. So if the rest of the array has 5 elements, it will make 5 steps. In fact, it will make 4 comparisons. Yeah, so we have this situation here, and this situation, the inner loop will make 4 comparisons to find out that this is the minimal value. Yeah, and this holds regardless what the initial ordering of this array was. And in all cases, it will make it will shift this yellow bar, this vertical yellow bar, from the left to the right of the array. So so increasing the sorted part and decreasing the size of the unsorted part of the array. So it's very easy to understand what's going on. So in this slide, I just summarized that, well, the best case is equal to the worst case, and which is equal, obviously, to the average case. There is no difference between all those cases. Yeah, so if we just try to count the comparisons, so in the first iteration we make n minus 1 comparisons, in the next iteration we make n minus 2 iterations, and so on. So in the final iteration, so the last one, we have 0 comparisons because there's only 1 element left, and as a consequence we have this sum n minus 1 times n over 2 many comparisons, which is approximately n squared over 2 many comparisons. So this is a lot. Yeah, you might remember that insertion sort needs n squared over 2 many comparisons in the worst case only. Yeah, in average it takes just the half of this figure, and so it seems that insertion sort is better. However, there is one thing that is really nice in case of selection sort, namely the number of exchanges is at most n minus 1 many exchanges. So with each iteration of this outer loop, there's at most one exchange operation enabled here, and so with each so we make at most n minus 1 exchanges. So selection sort is actually not a sorting algorithm that you should use in a standard setting, but if you have something to sort where the exchange operation is substantially more difficult than the comparison operation, then you should go with selection sort. So namely, the only benefit of selection sort is it's optimal with respect to the number of exchanges, and it's actually worse than insertion sort and more or less all the other sorting algorithms with respect to comparisons. So in practice, why would you use selection sort? Just imagine that you have a parking lot with, let's say, 100 cars, and you have to sort the cars. You have access to all the cars, and you have to sort those cars, and you have only one square parking space. So there's only one place over, and so let's say 100 parking lots and 99 cars. And now your boss is coming to you and tells you, okay, please sort all those cars with respect to the plate of the car. So then it's actually, then what you should do is selection sort, because finding out what is the smallest plate number of a car is quite easy. You just have to consider all these cars. It's easy to see. But if you want now to do the exchange, then you have to do a lot. Well, then you have to do a lot of work, especially if these cars are lorries or whatever. So then it's expensive to swap, but it's cheap to compare. So if this is the case, then you should do selection sort, and this is the only case where you should do this.